Okay, let's go ahead and get started. We've got our volume back, so that's good. Our question of the day last time had to do with how you listen. It was kind of apropos, given that we had a problem with the microphone last time. So that was kind of interesting. I guess those of you with headphones and earbuds probably had the best time last time, because you can still kind of hear. I think I listened with speakers, and I was having a little trouble hearing myself from the recording last time. I wanted to mention a few things. So homework 8 I discussed on Wednesday. Lots of useful stuff in that lecture if you haven't seen it. There is a bonus for homework 8 that I mention here, and I posted it today. It's like the bonus for homework 4 in that it's a lot of work for not many points, so it's not something that I'm offering as a way for people to try to raise their score so much as something that for those of you who have an interest and have the time that you might want to explore. So it's worth 2 points. Basically, the idea of the homework 8 bonus, currently you produce 2 different files. You produce a code file and you produce the compressed file for Huffman. And if you lose the code file, for example, then the compressed file is useless to you. So you've got to have these 2 things. I mean, imagine if a utility like zip said to you that it's going to produce 2 files on your computer. You wouldn't be very happy with it. And it would be easy to lose one. So in the bonus, basically the code gets incorporated into the compressed file. So it produces 1 file as output instead of 2. So it's a little closer to something that would be a real practical utility that somebody might find convenient. So that's the assignment 8 bonus. It's due at the same time. It's that last Sunday, 11 p.m. That's a week from this Sunday at 11 p.m. That's when Huffman cuts off. That's the last time you can turn in Huffman, and that's when the bonus is due. And there's no extensions beyond a week from Sunday, so be sure that you get things done. I have posted final exam resources. I'm going to say just a little bit about it in a minute, but I wanted to kind of let you have a peek at the structure of the test along with a sample test. So I know some people are curious about that, so you'll have a chance to take a look at that. Here's what I would like to have happen. So I'd like you to be finishing up the Huffman assignment and getting ready for the final exam. So I'm going to show you these resources today with the sample final. There will be a second sample final that we discuss in section next week. So we're going to be kind of shifting into final exam mode. Friday of next week, on our last day of class, I'm going to do a review for the final. So I'm going to kind of go through question by question and talk to you about different kinds of issues that come up, things that you might want to be thinking about. So that's why I say I think it would be best if you didn't try to do the final next week, kind of save the final for the week after, for finals week. But I know that some of you have tight schedules. You have kind of your own issues in terms of stuff that you have to get done. So I want to try to be flexible for students like that. So I am going to release the final exam on Monday. So that's a holiday. We won't be having class that day. But on that day, you'll see that it'll show up, that the final exam will be available. Just like with the midterm, there'll be the exam and there'll be a key, and it's, the honor system. It's not helpful to you to look up the key, first and then do the exam. The whole point of this is to give you some feedback about where you're at in terms of the material from the course. So we'd like you to have the experience that's like the normal experience of studying for the exam, taking the exam, and then you could kind of take a look at the key afterwards. You'll set up a meeting with your TA to have a 15-minute discussion, say, about how you did on the final. So again, my recommendation is finish up Huffman and be getting ready for the final next week and do it the week after, but it will be released on Monday. In case anybody really needed to do it earlier, it will be available to you. All right, well, let me show you just in terms of what I've posted so far. So there's a little table that shows you the structure of the test. So there's a question where you're asked, here's a binary tree, tell us the 3 traversals. Here are some words or names or something. Show us what you get when you build a binary search tree out of that. A collections mystery problem where you're reading code to tell us what it does. Highly likely that that'll be 2-dimensional, a 2D array. That was something the TAs would have mentioned to you yesterday in section. There's a 10-point binary tree question and a 20-point binary tree question. 10-point binary tree question tends to be a traversal. The 20-point question tends to be one that involves changing the tree or building up a tree. Collections programming, there's kind of a 5-point collections programming and a 10-point. And then comparable class is an entire class, and linked lists. This is where we ask you to write a linked list code. The cheat sheet is kind of interesting in that you can use it as a way to know for the collections questions, this is what you're limited to. You're only allowed to use the things that are on the cheat sheet, but that also kind of gives you an indication of the things that you might be asked to use. This is kind of, the cheat sheet is a good thing to be looking at in preparing for the final, to be thinking about whether you know how to use the different things that are mentioned here, because they might be relevant for the question that we give. A sample final and a key to the sample final, and then the old exam questions is also available. The questions, not the answers. So anyway, a bunch of resources that you can start taking a look at. I mentioned, Monday is a holiday, so we don't have lecture that day. TAs will not be holding office hours that day. The university is officially closed that day. Wednesday of next week, I'm going to be giving a lecture on a topic called hashing. It's a really interesting topic, so I really hope that you guys will watch that lecture. And as I said, on Friday, I'm going to talk about the final exam, do a bit of a review for the final, and say a few things about life after 143. So that'll be Friday of next week. Today, what I want to do is I want to talk about this idea I've been mentioning all quarter long, that I had said that array Intlist and linked Intlist were a kind of case study that I wanted us to get to the point where we understand better how the built-in array list of E and linked list of E work. Now, that's professional code. It's complicated. I think it's unrealistic to imagine that we've gotten you to the point where you would understand all of it. But I think we've gotten you to the point where you can understand a fair amount of it. Today, I want to talk about some issues related to that to kind of flesh out what we've been discussing and talk about some object-oriented programming issues, some design issues. And on the calendar for today, I'm going to post a kind of a final version of these different classes for you to take a look at in case you're interested. So this is kind of our last object-oriented discussion today, is we're going to kind of talk about the final versions of array Intlist and linked Intlist. Now, we've been talking about interfaces, and so, the idea, array Intlist and linked Intlist, the built-in ones, array list of E, linked list of E, both implement an interface known as list of E. And so here I have, for our int version of things, I have an interface here known as Intlist. And it doesn't have all of the things that are included in the list of E interface, but I included enough things that I thought it was a representative sample of what was in the list interface that you would be interested in. Now, we had a discussion when we were looking at those shape classes. There was an interesting issue that came up that maybe there's some code that you would want to write once and apply to all of the different shapes. So we had a toString method that was that we eventually had as an inherited method, and there was a compare_to method that we wanted to have be an inherited method. And what we did in that case is, because we wanted to have some actual code, not just these headers for methods, not just the kind of the hollow versions of methods, but some filled-in versions of methods, we decided to go with an abstract class. That way we could avoid the redundancy. Well, so should we do that here? That's kind of the question. And that's an important question, is should we not be using an interface? Should we be using an abstract class? Well, remember what I said at the beginning of that lecture, that if you can do something with an interface, just an interface, you should do it with just an interface. And what would be the reason for wanting to do that, to use an interface instead? Well, it's because you can only have one inheritance relationship, but you can implement as many interfaces as you want. So we decided that there was some benefit by having these inherited methods, so we switched to having an abstract class. We went from having an interface to having an abstract class. This is one of these cases, and this is a classic thing in engineering in general and software engineering, in this case in particular, that there are trade-offs involved in different decisions that we would make. So there are advantages to the interface approach, the main advantage being that we don't burn your inheritance relationship, that you can have whatever inheritance relationship you want. The abstract class has benefits to it in that we can write code once that's inherited, and then we don't have to rewrite it, in multiple classes. So which one is more important? The avoiding the redundancy or being able to not specify their inheritance relationship? Well, Joshua Bloch was, I've mentioned to you, as kind of a Java guru. He was at Sun at the time that they were reworking all of these different collections classes. And what Joshua Bloch decided is that he would do both. So let me show you kind of a picture of, an indication of applying those ideas to our array int list and linked int list. So we're going to have an abstract int list class where we write code that can be written in common between the two different classes. So if there's something that's not specific to an array implementation or to a linked list implementation, then we'll include it in the abstract class. That way we can write the code once and inherit it in both of those classes. So we will have an abstract class that kind of factors out the common code, but we'll also have the interface. And what that means is that if you came up with your own fancy list, you have your fancy int list that you wanted to make part of our structure, you wanted to fit into our framework here, well, you can have your fancy int list class extend an abstract int list if you want, and then you would inherit some methods that have already been written for you, but you're not required to do it that way. You could instead have your own inheritance relationship. Maybe your fancy int list class inherits from fancy abstract int list class. Maybe you feel like you have a better abstract class or some other reason. But in any event, you can have your, whatever inheritance relationship you want, but by providing you with the interface, you can implement the interface. So if you're trying to introduce another class into this collection of classes and have it work with them, you can do that because we did things with interfaces. So you can use the abstract class if you want, but you don't need to. You can use the interface instead. What you'll see is that in java.util, so if you look at the list of things, that's where the collections framework it appears in the Java class libraries. You'll see that, especially when you go to the documentation, the internal documentation, and it shows you the alphabetized list, you'll see that the abstract, there's a whole lot of them at the very beginning, that there's an abstract list, there's an abstract set, there's an abstract map. In fact, they decided that lists and sets had enough in common that they have another layer to this where they have something called a collection. So there's an interface known as collection and an abstract collection class, and then both list and set extend collection. So that way they can factor out the common things between lists and sets in something known as a collection. So there's an extra level of structure in their hierarchy. And so you'll see a whole bunch of these abstract classes there, and you'll see a whole bunch of these interfaces, and you'll see a bunch of implementations. So this pattern is followed in java.util. You'll see it used kind of throughout that framework, throughout that set of classes. And so this is a useful thing to understand. Even if you don't want to understand how they're written, you just want to be a client. then you kind of want to understand what are these abstract classes, why are they there, you want to understand the thought process behind how this framework was put together. So this picture is a useful thing to understand that this is a general idea that we want to have an abstract class to factor out common code, but we also want to have an interface in case you want to bypass the abstract class and have your own inheritance relationship and implement the interface instead. So what I want to do today is I want to write a few kind of representative examples of this. So imagine that what we're going to do is we're going to make an abstract class called abstract Intlist, and it's going to implement our Intlist interface. So the question to ask yourself is, are there methods here in this interface that would be good candidates for including in the abstract class? Let me give you an example of a method that is not a good candidate. How about the get method? So think about the get method. Well, we wrote the get method for both of these implementations. And so for the array Intlist class, the way that get was written was that we returned element data of index. That we had an array and it has an indexing scheme. And that's so super easy with the array Intlist is that we just went right into our array to that spot in the array. What did we do in our linked Intlist class? Well, there what we had to do, since we didn't have an indexing scheme, they're not in an array, we had to kind of start a counter at 0, start at the beginning of the list, and we had to go next, 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 kind of go through the linked Intlist until we got to the appropriate spot. We'd have our counter go up, so until we got to the spot we were looking for. So very different implementations of get, because they depend deeply on the implementation, on the structure that you're using for the implementation of your list. So get is not a method that we would expect to have in the abstract class. It's almost the poster child for the method that would never be in the abstract class because it is so dependent on the implementation. There's similar things about add, for example, that we had the appending add and the added in an index. So those are very specific to the kind of implementation. In the array implementation, you're putting something in an array. In the linked list implementation, you're inserting a new node, so very different kinds of implementations. But what about add all? So add all is an interesting case because we can build add all on top of the add method. So let's do that. Let me write some code here. So what if we wanted to have a public void method called add all, where we're going to take an int list other that we want to, the idea, we've mentioned this idea of add all. By the way, add all and remove all are methods that are on the cheat sheet for the final. These are things that you would want to be aware of, for the final exam, because they might be things that you would want to use on the collections questions. Add all. So the idea would be that I give you some other list and I want to add everything that's in that other list. Or like if there's 8 things in that other list, I want to add those 8 things to the end of my list. So we do want them to go at the end, and so we can use the appending add command. We can use our own add command to do that. But then how do we kind of get the 8 things? Well, we want to traverse that other list. How do we traverse a list? So with an audience, I normally ask, how do we do a traversal? And I think people are so used to, ever since chapter 7, when I talked about, the standard loop traversal, people are pretty good about saying, well, we could do for int I equals 0, I less than other.length if this were an array, but this isn't an array. This is an array int list. Now, could we, it's an int list. What I just said was exactly wrong, because I wanted to say the following thing. So can we say other.size semicolon? That would assume that size was a field, and we don't get to make an assumption like that when we're working with this abstract class. All we know about an int list is that it has the methods that are mentioned here. But there is a size method. We don't necessarily know how that size method is implemented. But we know that there's a size method, so we can use that, and we can do I++. And then we want to call our appending add method, and we want to add the ith thing from the other list. Well, you know, that's going to be very different depending upon the array implementation or the linked list implementation, but we can use get. So we can say, get me the ith value, and I want to add that. Oops, I think I had enough right curly braces there. So I want to append to the end of my list the other list's ith value. So I use the size method and the get method as a way of doing a standard traversal of a list. It works. I mean, this code would be code that works for both of them. It doesn't refer to the implementation, so we could kind of say that's what we wanted to do. But it turns out that this is not a good solution. I'm going to comment it out. So here's the issue. We are trying to come up with code that would go into the abstract Intlist class, code that will be implemented, that will be inherited by these two classes, and we'd like that code to behave well in each of the two classes. That's not always possible, but here there's this very specific thing I want to be talking about that's worth thinking about. So how is this code going to work? This code is very similar to the Chapter 7 code for arrays. In fact, this code works really well on an array int list because size and get are methods that execute very quickly. But what about a linked list? Well, I'm going to show you a nicer implementation of linked list that stores a size. So size will be quick. You know, we can ask for size very quickly. But what about get? How is get going to work in a linked int list? Well, I mean, and what if the list is big? So like, what if it has 10,000 things in it? And we want, you know, we're adding maybe 10,000 things from some list. Suppose, for example, that I has gotten up to 5,000. Then what are we going to do to get the 5,000th element of this other list? We would start at the beginning and we'd go next, 5,000 times. To get that value, we'd return it, and then we'd add it. And then what does it do? It goes back around the for loop. I gets incremented to 5,001, and we say to the linked list, get me your 5,001st element. And it's like, you just had me get the 5,000th element, and I've already forgotten where it was. So now it has to go all the way back to the beginning and do next, 5,001 times to get to the 5,001st element. So this is going to turn something that could be an O of n operation into an O of n squared operation, because it's going to get slower and slower and slower to call the get method as I gets larger. So this does fine for an array int list, but it's super slow for a linked int list. So we'd like to find an alternative if we can. So what would we do? I get various kinds of suggestions here. One of the suggestions that people make is they say, well, think about it. You know, if I knew it was a linked int list, if I knew I was going to be working with a linked int list, and I knew I was going to be doing something like this, then I could just have a reference into the list, right? And so if I was at the 5,000th element, I could kind of keep my pointer there, and then when I wanted the 5,001st, I'd just move my pointer over by 1. I'd just kind of, current gets current.next. I'd move it over by 1, and then I'd have the next one available to me. And if I remembered that, then I could do current gets current.next again. It would be really fast for me to kind of move to the next thing. Well, the problem is we're working with an abstract class. We don't know that it's a linked int list, and we don't know anything about nodes. Nodes are private things within a linked int list class, so it doesn't quite work out. Well, I often at this point get people to say something like, would an iterator be helpful? So how do we declare iterators that work with lists of ints? Remember that it would be an iterator of integer would be the type that we would use. So is it possible for me to ask the other list to give me an iterator? Can I use an iterator to move through the other list? Well, the first thing you'd have to ask yourself is, this other is of type Intlist. What do we know about an Intlist? That it has all the methods that are listed here. So do you see an iterator method listed here? I don't. So this doesn't work. It's not going to work. But, you know, let's take it as a suggestion that it would be good to have a public method that returns an iterator of integer called iterator. So let's add it to the interface. Let's decide that that's going to be something that we require, is that you give us an iterator. Now, we spent time in a lecture talking about how an iterator would be implemented for an array int list. And at the time, one of the things that I mentioned is that we're used to writing code with array int lists where we have an int I, and we're saying array bracket I, and we're doing I++. And and the way that our iterator was implemented was that the iterator was basically that int I. It was an integer index that kept track of where we were in our list, initially 0, but then it kind of got bigger as we went on. And so when we did things like next, we told the iterator next, it would use the current index to get a value, and then it would do an index ++ to be ready to return the one that comes after that one. And so that's kind of how it was implemented. The array-based iterator. Well, we didn't talk about how to do a linked list-based iterator, but let me just kind of mention briefly how that would be done. Well, how do we manipulate linked list code? Well, that's with like a list node current, right? We start a current at the front of the list. In the same way that we started an int I at 0, we start a list node current, at the front of the list. And we do current gets current.next, current gets current.next. We see whether current has become null, is there anything left. That's how we write loops that traverse through a linked list. So a linked list iterator is basically like that current. In the same way that the array int list iterator was int I, was kind of what was in the iterator, what will be in the linked list iterator is a list node current. So the iterator will kind of initially be referring to the first node in the list, but then as we tell the iterator, remember that the iterator, the iterator interface said that it had these 3 different methods where we would do has next, next, and remove. And so, has next, we see whether there's anything left, has it reached the end of the list? And then when we go to do next, we use the kind of the current node that it's pointing to, get the data out of that node, and then set the current to current.next. So that's that's the way the iterator code would be written. So we do want to have an iterator as part of our abstract class. And given that we'd have an iterator, we could do something like this. We could say, while the iterator has a next value, the way that we get that next value is by calling next, i.next. In some cases, what I did was I stored that in a local variable, which would be a fine thing to do. If you're going to do more than one thing with this value, then you basically have to store it in a local variable. This is a case where I actually don't need to do more than one thing. All I want to do with this value is to call add, is to append it to the end of our list. So I'm going to just add and then not store it in a variable, have the i.next here. By the way, today's lecture, people say, is this on the final? It is and it isn't. I'm not going to ask you about abstract classes and all of this kind of stuff. So, a lot of this is for your own information and for those of you who like understanding these things at a deeper level. But a lot of what we're going over here are things like manipulating iterators and stuff, and that's definitely on the final. So, you could think of this as a bit of a review of some iterator manipulation. We would ask the other list for its iterator. For an iterator, we would, while it has something more to give us, we keep calling next, 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 and then we call add on that. So in the array case, that iterator is keeping track of an integer index, and next, 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 next is doing I++, super fast. In the linked list case, it's keeping track of like a list node current, and it's setting current to current.next, keeping track of where it was last. So that's going to be fast as well. It's not going to have this problem of, it's at element 5,000 and it has to start back over at the beginning again. The iterator will keep track of where it is. So this is the way that I would write that code, assuming that we had an iterator available to us. Now, some people suggest, they'll say, well, we had even another way of doing this that we liked. So let me comment out this version and mention that another way of doing it is with a for each loop. So you could say for all of the integers n that are in that other list, I want to add n to my list. That's certainly a nice way of writing it. The for each loop is simple syntax. It's kind of easier to write the for each loop than it is to write the iterator code. I hope you guys are taking advantage of that and using a for each loop, whenever it's appropriate, because it's just simpler. It's nicer. There's less likelihood that you'll make an error, and you certainly can use it on the final to do for each loops. All of those structures that we looked at have for each loops for them. Now, we can't do that in this case, at least not yet. So the issue is that that Java does not give you a for each loop for free. So Java has a particular kind of rule about what you can do a for each loop for. It has an interface known as iterable of t. Notice that lots of things implement iterable of t, including various lists and sets and so forth. What it says is that the method that you need to have is a method called iterator that returns iterator of t. If you have such a method, then you can claim to implement the iterable interface. So can't I come over here and say that this implements iterable of integer? What does it mean to implement iterable of integer? It means that you have a method called iterator that returns an iterator of integer. So in fact, adding a little clause in the header like this means that I don't have to list this here, because that's what the clause means, is that it says, that in order to be considered to be something that implements iterable, you have to have a method called iterator that returns an iterator of integer. But remember, this is an interface and this is an interface, and I mentioned in that lecture where we were talking about the shapes that you use the keyword extends here. That's a little obscure detail of Java, but when when they're both interfaces, then we say extends instead, the way we do with an inheritance relationship. So we can have our Intlist interface also require that it implement the iterable, which requires that we have an iterator method. And once we've done that, then our Intlist is iterable, and then the for each loop works. So that's how you tell Java that your class is going to be something that supports the for each loop, is you implement the iterable interface and then it works. So that's the code I'm going to leave us. That's kind of the end code. That's the nicest version of this. And what a for each loop does is it's implemented using an iterator. So it's going to be efficient. It's going to be as efficient as the iterator code, and it's a little simpler to write. All right, a few more things I wanted to go over then. What if we wanted to think about how to write the remove all method? So that takes an int list other. How would we do that? So we actually did something like this. You may have forgotten by now. It was way back, I think, in lecture 4, where we did a remove all for the array Intlist class. So it was specific to the array Intlist class. And we talked about different possibilities that you could iterate over the other list, kind of looking at all the different values of the other list, and then trying to find things in our list that match that. Or you could kind of focus on our list, kind of go through the things in our list, looking to see where the things were in the other list. And I discussed at the time the fact that it's a little easier to kind of iterate over us, to think of it that way. Sometimes I get a suggestion from students that they say we should do a for each loop to go over us. That's an interesting case. You could do that. You could say for all the integers n that are in our list, how do you say me? How do you say all of the things that are inside of me? That's what this keyword is for. It's the implicit parameter. It's the reference to the object that's actually executing, that's doing this method. So, we could do something like this and then have some code inside of here. But remember that there's a limitation on the for each loop, and you want to remember this for the final. If you are changing the structure, then you can't use a for each loop. So a for each loop is a read-only type operation. So it's an interesting idea, but we don't want to be using a for each loop here. This is a case where I think it really does make sense to use an iterator. So let me have an iterator of integer I, and I want this to iterate over us, so I'm going to call our iterator method. It's basically calling this .iterator. I'm iterating over this object. And what I can say then is, while I.has a next value, I can say, let's go ahead, this time I'll put it in the local variable, int n equals I.next. So I could go ahead and do that. Now, what do I want to do? So I'm iterating over the values that are in my list, and the idea is for me to remove from my list anything that appears in that other list. So what do I want to know? I want to know if this thing is in the other list. I could loop over the other list looking for it, but remember, we've got lots of methods available to us. Included in these various methods that are here is a contains method. This is the kind of thing you're going to want to watch out for on the final as well. This is why it can be helpful to you to review the cheat sheet to remind yourself of the different methods that are there. I can just say if the other list contains that n, then I know that it's something that I want to remove. So remember that there's a contains method, and we can call it. I can see whether this n that's in my list is also in the other list, in which case I want to get rid of it. Well, so you might imagine that I could somehow remove that n, but the remove command removes at an index. You remove at an index, not remove a value. So we'd have to somehow know the index. But it's even worse than that. There was an important thing that I mentioned that I want to remind you about, because it is very relevant on the final, which is that if you are iterating over a structure, you are not allowed to change the structure without talking to the iterator. So this was an issue where we got a concurrent modification exception. So we don't want to be talking to the iterator and then also talking to the list in order to have the list do a remove type command, because then the iterator notices that someone else made a change that wasn't a change that it made, and so it gets upset and it throws a concurrent modification exception. This is something you do need to know for the final. So what we would want to do here is we would want to remember that back over here, the iterator code, the iterator has a remove method. So if you're using an iterator to go through a structure and remove things from the structure, you have to let the iterator do the remove. So we would tell that iterator I to remove the most recent thing it had shown us in a call on next. So it's going to remove this n, that we were just being shown. And so I can close that, close the while loop here, and now that's generic code that would work for either the array int list or the linked int list. It's using the iterator to kind of do the removing from the structure. So that would be an example of how we could do a remove all. And that's kind of what I wanted to show you, was to have a couple of simple examples there. I think that what I want to do is I want to show you the final solution. I want to point out some aspects of this final solution. Now, there's a lot in these final solutions. So I did want to end the quarter by showing you a higher quality version of these two classes than what I've shown you before. But don't worry about what I'm about to show you. you could think of this somewhat as being, now would be the time for you to say, is this going to be on the final? And the answer is no. I'm not expecting that you are going to understand what I'm going to talk about in the next 10 minutes, where I'm going to kind of point out to you some of these features of the final version of the array Intlist and the linked Intlist. But I think that several of the things that I'm going to point out should be relevant, are things that you could understand. And that you might find interesting to kind of have a better sense of what's going on. I mean, I've said all quarter that we don't quite get to finish object-oriented programming, so some of the things I'm going to show you are things that we just haven't had time to talk about. But that's, we fit in as much as we can in a class like 143. So the abstract Intlist class. So that's here. Kind of the question is, how many of these things from Intlist was I able to write a generic version of? Well, I was able to do the toString method using an iterator. I was able to do index of using a for each loop. IsEmpty, I was able to do with an iterator. Contains used index of to be able to figure out whether something was there. There's the add all code that we just wrote with the for each loop. There's the remove all code that we just wrote. I can even have a little code here that was checking the index. That was where did we have? The index is, so actually this is an interesting case. Maybe this is worth mentioning briefly. I don't always mention this, but I have a little more time today than I normally do. This has a keyword we haven't seen called protected. Protected is a different kind of limitation. Private means only things in this class can see it. Public means anyone can see it. Protected means that subclasses can see it. So this is introducing a check index method that both the array Intlist class and the linked Intlist class can use. Now where this came from is that I found that I had this method, I was using this method in both of these classes because these classes implement get at an index, add at an index, so I needed to be able to check the index. So instead of having that method appear, copy-paste two different versions, in the two different classes, I've elevated it to be in the abstract class, but they wouldn't have access to it unless I made it either public or protected. I don't want to make it public because I don't want to make this something that a client would see, so protected. And as I said, if we had more time, we'd be talking more about when to make something protected. Joshua Block is a fan of protected methods, of kind of making some methods in the higher level class that are available to your subclasses. So you're kind of giving some capability to your subclasses here. So that's what that check index is. So array Intlist then extends the abstract class. So that means that you'll find that it doesn't have a toString, it doesn't have an index of, it doesn't have a contains, because those are all inherited. So it does have a get method, it does have constructors, so it has a lot of the, a size method. So it has those details, that we've seen before. There it's using that check index method that is the protected inherited method. So that's kind of this very specific code that's specific to this implementation. But I want to show you something else that's here, which is there is a class inside the class. So when we did the iterator class, we did the iterator as a separate class. So there was kind of array Intlist and there was array Intlist iterator. That's not how it's normally done. The way that it's normally done is this way, where the iterator class is inside the other class. So we have a thing called array iterator, which is a class, private class, that's part of the implementation. That's why I make it a private class. I don't want people outside of the class to be using it. So we have an array iterator that's here. Now, you may not remember the code that we wrote. This version of it is simpler than what we wrote originally. Let me just kind of point it out to you in the following way. So it's keeping track of a position. That's its basic thing, is the int I. It's keeping track of an integer position. And how does it know whether there's anything left to traverse in an array list? It sees whether that position is less than the size. So it's calling here a size method. But the iterator doesn't have a size method. So whose size method is being called? So that's kind of a mystery. Well, and this is a detail. Again, if we had more time, we'd be talking about this. When you put a class like this array iterator class, inside of the array Intlist class, then the inner object has access to the outer context. In particular, an array iterator has access to all of the fields and all of the methods of the array Intlist object that constructed it. So it can, I could even have used a field here if I wanted to instead of a method. But basically, iterators then can kind of refer to this outer context directly, which is a very powerful thing to be able to do. It does mean that there are some weird confusions that come up, like in the case of removing something, there's kind of two removes. There's a remove in the iterator, because iterator has a remove, and there's a remove in the outer class, the array Intlist class. And so here I had to use a kind of a weird notation where I said that the remove that I want is the array Intlist's remove. So it's the array Intlist.this. So there's kind of two thises. There's a this for the innermost object, which is the iterator, and then the outer this, which is kind of the this for the array Intlist. As I said, this stuff is complicated. I don't expect you to be understanding all of it. I'm trying to kind of explain it as best I can and hope that you get something out of the explanation. I want to show you the linked Intlist implementation as well and tell you a few things about it. So I'm keeping track of a size. So I said that any sane implementation would keep track of the size. And what I decided to do was to keep track of both the front and the back. So I can do quick things at both the front and the back of this list. This linked int list has nodes that have links in both directions. There's a next, but there's also a prev. So we refer to this as a doubly linked list. So I didn't want to make you deal with the complexity of a doubly linked list, but that's what this one is. And that's like the built-in linked list in Java. It's kind of a more common thing, is to do the doubly linked version of the list. So there's interesting issues about that, like what are the elements of the list we can get to quickly? Well, like if we were calling a get command, that you start at the beginning and you go next. It could take a long time to kind of get something that's far along in the list. But because we have a reference to the back and we have prev, we can also access things at the end of the list very quickly. So actually, we can go from either end, to kind of get somewhere. So the thing that takes the most amount of time to get to is the middle value, whatever's in the middle of the list. And you'll see that I have some code here. So for example, I have a method here that gets me a value at a specific spot. So there was an add, a get, a size, linked int list. Node at is the method that I was interested in. It looks like I have that a ways down. Oh, there's the iterator. There's node at. So it's a private method. So it kind of says, is this thing in the first half or in the second half? So it either starts at the front going forward or starts at the back coming backwards. So there's some interesting code for that. Now, I wanted to show you that there's an iterator class here as well, inside of this class. And so that means that it can refer to things like front.next. That's a reference to the field. It's the front of the linked int list object that constructs this iterator. So it's very useful. It's important with the linked version of this to have kind of this inner class that's able to deal with referring to things like front and back. Now, I mentioned to you that when you have a class like this, this thing has access to the outer object. Well, how is that implemented? The way it's implemented is that all of the objects of this inner class have a reference to the outer object. They store an extra link to the outer object. Well, that's kind of expensive, that if each one has a link. Think about nodes. You might have 10,000 nodes. Do you want all 10,000 of them to have a link to the list that constructed them? In general, the answer is no. So what we do for our list class is we add an extra little identifier there that we make it a static inner class, and that cuts off that connection. That means it doesn't have the connection to the outer object. But we've been talking all quarter about nodes being visible only in the implementation. A client from the outside wouldn't even know this class exists because it's an inner private class. All right, well, that was a lot of stuff. It'll be on the calendar for today. Have a good 3-day weekend, and we'll be back.